Rules of differentiation, part 1. Before we begin, let's make sure we're all on the same page. Which of the following is false regarding a derivative? 1. It tells us the rate of change between a dependent variable and an independent variable. 2. For nonlinear functions, it is a function itself. 3. When evaluated at a particular value of x, the derivative is the slope of the tangent line at that x. 4. It describes the shape of a graph. 5. It's the slope of the secant line between two discrete points. And the answer is 5. Everything else is true regarding a derivative. It's the rate of change between y and x. For nonlinear functions, the derivative is a function itself. When we evaluate the derivative at a particular value of x, it's the slope of the tangent line at x. And because a derivative is just a slope, of course it describes the shape of a graph. The thing that's false is that it's the slope of the secant line between two discrete points. So given any continuous smooth function y is equal to f of x, we can use derivative rules, which are just formulas, to find the derivative at any point. So in other words, using calculus rules, we can determine the slope at any point along this curve. So this curve is y is equal to 10 plus 3x squared. So for example, using what's called the power rule, I can say that the derivative of this function is 6x. So for example, at x equals 0, the derivative is 0. At x equals 1.5, the derivative is 9. And at x equals 3, the derivative is 18. So it's a lot easier and quicker to use derivative rules rather than going through the limit approach, which is what we did in the previous lecture. So instead of calculating the slope and then taking the limit of this slope by letting the change in x approximately equal 0, we could have just used what's called the power rule to say that, for example, when y equals x squared, the derivative is 2x. So differential calculus provides rules, or just formulas, that allow us to calculate these rates of changes of variables in an elegant and simple and concise way. And there are several rules that we use in economics: the constant rule, the power rule with a coefficient, sum and differences rules, product and quotient rules, and the generalized power rule which is a subset of the chain rule if you've ever heard of the chain rule before. So in the first part of derivatives rules, we're going to focus on these. We're going to focus on the constant, the power rule with the coefficient, and sum and differences rule. Let's begin with the constant rule. A function of the form f of x is equal to b, where b is a constant, is called a constant function. The graph of f of x equals b is just a horizontal line, and a horizontal line has 0 slope. So we would expect that f prime of x is equal to 0. The constant rule tells us that if y is equal to f of x is equal to b, where b is a constant, then dy dx is equal to 0. Quiz yourself. Find and interpret the derivative of each of the following functions. F of x is equal to -5, f of x is equal to the square root of 3, and f of x is equal to 9 million. Pause the video and try this yourself. So for each function, f prime of x is equal to 0 according to the constant rule. Now find and interpret the derivative of each of the following economics functions. Total revenue is equal to 10, total cost is equal to 400, and quantity demanded is equal to 50. Pause the video and try this yourself. Because each function is really just a number, just a constant, each derivative is equal to 0. This is saying, for example, in regards to total revenue, that if quantity increases, total revenue remains the same. If quantity increases, total cost remains the same. If price increases, quantity demanded remains the same. Now let's move on to the power rule with a coefficient. A function of the form f of x is equal to b times x to the n, where n and b are constants, is called a power function. The b is a coefficient. It's also called a constant or a scalar. So, power functions include f of x is equal to x, which is just saying that n equals 1, and radical functions, where we have a fractional n, so n equals 1/2. The graph of a power function is nonlinear. So here's an example of 3 different types of power functions. The power rule with the coefficient states that if y is equal to f of x, which equals b times x to the n, where b and n are constants, then the derivative of y with respect to x is equal to b times n times x to the n minus 1. So when it comes to the power rule, what you're doing is you're pulling down that exponent, and then within the exponent, you're subtracting 1. Let's find the derivative of each of the following. Y is equal to x squared, y is equal to 1/4 x squared, y is equal to 100 over x, y is equal to the square root of x, y is equal to 20 times the square root of x. Okay, so we're asked to find the derivative of these functions using the power rule. So I'm going to write the power rule. Actually, I'm going to write it right over here, okay? So when we have a function that's of the form y is equal to b times x to the n, wow, what was that? That should just be an n to the n, then dy dx is equal to b times n, I'm just going to pull that exponent down, times x to the n minus 1, and then I'm going to subtract 1 from the exponent. So this is the power rule. This is what we're going to use. So if you're not used to this, this is what I suggest you do. Let's start with, I'm going to work over here. Let's start with the first one. So the first one says y is equal to x squared. So I'm going to define b, I'm going to define x, and I'm going to define n. And then I'm going to plug it back into my equation. So my b here, the coefficient in front of the variable is 1. X in this case is x, and n is equal to 2. So now I'm just going to use this power rule. And what that yields is 2 dy dx is equal to 1 times n, which was 2, times x, and then n minus 1, which ends up just being 1. And I simplify that and I get 2x. So now let's move on again. Let's go to the second one. Y is equal to 1/4 x squared. So my coefficient is 1/4. My variable of interest, what I'm taking the derivative with respect to, is x. And I'm writing this out because later on when we use economic functions, it may be something like L or it may be Q. So just get in the habit of doing this. The exponent, n, is 2. So according to the rule, dy dx is equal to the coefficient, b, times n, times the variable of interest, times the exponent, n minus 1. 2 minus 1. So when I simplify this guy, I get I get 1 over half times x. Perfect. Oh, and I'm leaving off the one, there's a 1 exponent here if you want to keep it there, but we generally don't write that. So let me just go like that. Okay, so then let's go to the third one. Y equals 100 divided by x. So this one's a little bit trickier. So my coefficient is 100. My x variable is my x variable. It's what I'm taking the derivative with respect to. And my n is actually -1. So let me write an aside over here for this guy. 100 over x is the same thing as 100 times x to the -1. Okay, it's the same exact thing. So this is my n. So now let's plug it into our power rule formula. Dy dx is equal to that coefficient times the exponent, which is -1, times the variable x. And I'm going to subtract 1 from the exponent. So I got -1 minus 1. So when I simplify this guy, I get -100 times x to the -2. And you can write that even further if you want. You can write is -100 divided by x squared. So one thing to keep in mind, just to remember, is that when you have something like 1 over x to the n, it's the same thing as x to the -n. These two are identical to each other, just different ways of writing the same thing. Let's move forward. With 4, y is equal to the square root of x. So there is no coefficient here. It's just 1. So there is a coefficient, it's 1. Sorry about that. The variable that we're taking the derivative with respect to is x, and our exponent is a half. So remember, the square root of x is the same thing as x to the half. Okay? So then, using the power rule, I have dy dx is equal to the coefficient times my exponent times the variable, all to the exponent minus 1, which yields, that's supposed to say 2, which yields 1/2 x to the negative half. So you can keep it like that, or you can write it like this, 2 to the x to the half, right? Same exact thing. And then finally, I don't have much room over here, so let's put 5 over here. B is equal to the 20. X is equal to x. And n is, in this case, is equal to 1/2 again. So I'm going to plug it into the formula. I get dy dx is equal to 20 times 1/2 times x to the 1/2 minus 1. And I can simplify this guy, and I get 10x to the negative half. You can leave it like this, or you can simplify it even further. It doesn't matter to me because the two are exactly equivalent. 10 divided by x, I don't know if you can see that. It's the same thing as 10 divided by x to the half. Quiz yourself. Find and interpret the derivative of each of the following functions. Pause the video and try this on your own. Using the power rule, we can find the derivative of each of the functions. If f of x is equal to negative 5x squared, then f prime x equals negative 10x. If f of x is equal to negative 5x, f prime x equals negative 5. If f of x is equal to negative 5 times the square root of x, f prime x equals negative 5 divided by 2 times x to the negative 0.5. And if f of x is equal to negative 5 divided by x squared, then f prime x equals 10 times x to the negative third. Sum and differences rule. A function may be written in two parts. F of x is equal to u of x plus or minus v of x, where u of x and v of x are both functions of x. In this case, the derivative of the sum of two or more functions, f of x equals u of x plus v of x, is the sum of the derivatives, f prime x equals u prime x plus v prime x. And the derivative of the difference of two functions, f of x equals u of x minus v of x, is the difference of the derivatives, f prime x equals u prime x minus v prime x. Example, find the derivative of each of the following. If y is equal to x squared plus 3x to the 9th, then the derivative of y with respect to x is going to be the derivative of x squared plus the derivative of 3x to the 9th. So it comes out to be 2x plus 27x squared. So I'm using the sum rule, but I'm also using the power rule. If y is equal to x squared minus 3x to the 9th, then the derivative of y with respect to x is going to be the derivative of x squared minus the derivative of 3x to the 9th, which turns out to be 2x minus 27x squared. And then finally, a little bit more complicated, if y is equal to 20 times the square root of x plus half x squared minus 10x, then the derivative of y with respect to x is going to be the derivative of that first element, 20 times x to the half, plus the derivative of the second element, 1/2 x squared, minus the derivative of that third element, 10x. Comes out to be 10 over the square root of x plus x minus 10. Find the derivative of each of the following functions. Pause the video and try this yourself. Remember that you're not just using the sum and differences rule, you're also going to end up using the constant and power rule. If f of x equals negative 5x squared plus 10x to the third, then f prime x is equal to negative 10x plus 30x squared. If f of x is equal to negative 5x minus 10x to the third, f prime x is equal to negative 5 minus 30x squared. If f of x is equal to negative 5 times the square root of x plus 2x to the 10 minus x to the fourth plus 15, then f prime x is equal to negative 5 divided by 2 times the square root of x plus 20 times x to the ninth minus 4x to the third, and then plus a 0. And finally, a quadratic function. If f of x, or general quadratic function, if f of x is equal to ax squared plus bx plus c, then f prime x is equal to 2ax plus b. Now let's find and interpret the derivative of each of the following economics functions: total revenue, total cost, and quantity demanded. Pause the video and try this yourself. If total revenue is 10q to the third minus q squared, then the derivative of total revenue with respect to quantity is 30q squared minus 2q. If total cost is 4q squared minus 2q plus 5, the derivative of total cost with respect to q is equal to 8q minus 2. And finally, the demand curve. So let's summarize every derivative rule that we've learned so far. First, the constant rule. If y is equal to f of x, which equals b, where b is some constant, then the derivative of y with respect to x is equal to 0. The power rule with a coefficient. If y is equal to f of x, which equals b times x to the n, where b and n are both constants, then the derivative of y with respect to x is b times n times x to the n minus 1. And then the sum and difference rules. Sum rule first. If y is equal to u of x plus v of x, where u of x and v of x are both functions of x, then the derivative of y with respect to x is just the summation of the derivatives. If y is equal to a difference of functions, in other words, if y is equal to u of x minus v of x, where u of x and v of x are both functions of x, then the derivative of y with respect to x is the difference of the functions.